Okay, when you find an inverse, remember you're basically swapping the x and the y coordinates. So it seems logical, hopefully, that the range of the original function becomes the domain of the inverse, and the domain of the original function becomes the range of the inverse. If we're swapping the x and the y, hopefully that makes sense. If the range is not all real numbers, then when you find the inverse of the function, you must include this information as a restriction on the domain of the inverse. Because otherwise you wind up working with imaginary numbers, and that's not good. So here's an example. Find the inverse. That's our goal. But first, I want to identify the domain and range of this function. So let's start with the domain. Actually, you know what? Let's try to picture what this graph is going to look like. What does the graph of a square root function look like? Yeah, it's kind of a half of a sideways parabola, right? I don't know exactly where this thing starts, but it starts somewhere, so I just put it there. Okay? All right. So now that we know that, is the domain going to be all real numbers? No, it won't. Because my graph starts here. What happened to all these numbers over there? They never got graphed. Why? But why? It gives us a negative value underneath here, and then when we try to square root that, we get an imaginary result. That's why the graph does not continue this way. So therefore, the domain is not all real numbers. We have to figure out what the domain actually is going to be. Do you remember how to do that from Algebra 2? Okay, then logic this through with me. If the numbers inside here become negative, then we are imaginary, right? If the numbers inside here are positive, then we are not imaginary, correct? So where should we find where the numbers switch signs? Set what's inside equal to 0, and that will be where the sign change happens. So I'll take, for the domain, I'll take the 2x minus 3 and set it equal to 0. And then solve for x. Add the 3 to both sides, divide both sides by 2, and x equals 3 halves. So now the question is just, well, do we want x values that are bigger than 3 halves, or do we want x values that are less than 3 halves? Take a look at what we have here. If I have numbers that are bigger than 3 halves, do I wind up positive or negative? Positive. So then the domain, therefore, must be x has to be greater than or equal to 3 halves. Because we can't actually be 3 halves. We can have the square root of 0. Okay, how about the range? How do I do that? Not necessarily. If you look at this graph, the range is the y values that are going to get graphed, right? And I can tell from what I know about square root functions, because this is a positive square root, that this thing is going to be upright like this. So that means that y values that are greater than wherever it starts are going to be my range. So where does it start? Well, how do I know it starts at 0? It does, but how do I know? How would I know the x coordinate right there? What is the x coordinate right there? It's 3 halves. How do I know it's 3 halves? Because we just found it, yeah. This is where the graph starts. So that is my starting value right there, 3 halves. Okay? So that means if I take my starting value and I substitute it into my function and I evaluate it, then I'll get my starting y value as well. And when I do that, in this case, I get 0. So the range here is y values that are greater than or equal to 0. Okay, so We want to find the inverse. We identified the domain and range already of our function. So now it says then the range becomes the domain for the inverse. So that means for my inverse function, the domain will be what? X is greater than or equal to 0. And the range will be y is greater than or equal to 3/2. Okay, so now that we understand that there is a restriction on the domain, when we find this function, we can apply that restriction to the domain. If we were to ask to graph it, then we would only be graphing x values that are greater than or equal to 0. It's incredibly important that you do this analysis before you try to graph something so that you can understand what the graph actually looks like. So let's go ahead and find the inverse of this guy. How do we do that? I can change the f of x to a y and then switch the y and the x. So now what do I have? 2y minus 3. Okay, so now what do we do? So yeah, we want to solve for y, which means we need to square both sides. And then, what do we get? X squared equals 2y minus 3. Add 3 to both sides, so x squared plus 3 equals 2y. Divide everything by 2. So I get, and I'm going to write this as separated out, 1/2 x squared, or x squared over 2, plus 3/2 equals y. Okay, yes, good idea. Turn this back into your function notation. This is f inverse of x equals 1/2 x squared plus 3/2. And I'm putting a comma in there, and I'm going to say yep, we have to include that restriction. X has to be greater than or equal to 0. So this is my actual answer here. Yeah, it is kind of a shoe. So what does this graph look like? It is a parabola. But it's only this side of the parabola. Where's the vertex? No, it's not at 0, 0. It's at 0, 3/2. If I think of this as vertex form, this is actually vertex form that it's in right now. Then I have a dilation of 1/2. It's an upright parabola. The h, the horizontal shift, is 0. The k is 3/2. So my vertex would be up here. And then it's been dilated by a factor of 1/2, which makes it look a little bit fatter than normal. So there's my graph. I'm not drawing this side of the parabola because that's not in my domain. And if I include this graph, the original, then you can see the sort of reflection over the line y equals x, just like we were talking about before. Question, does sine x have an inverse? I'm giving you the graph there. Your answer is no. Why not? Yeah, it doesn't pass the horizontal line test. So the answer here is no. Clearly I can draw a horizontal line on here and it's going to pass through my function more than once. Yeah, that's right. So technically there is no inverse for sine. But could we restrict the domain on sine so that it passes the horizontal line test? Yeah, we could. So to generate an inverse for sine, we have to restrict the domain. And if we do that, then it will pass the horizontal line test, and therefore it will have an inverse. So, can we restrict the domain somewhere? Negative this to positive this. We have to be always increasing or always decreasing. So in this case, for sine, if I start at 0 and I go to pi, I increased and then I decreased, so that does not work. If I start at a peak and I go all the way down to the valley here, then I decrease the entire time. And therefore, I would have an inverse. But what we're going to do is define from here to here as the domain restriction. So if I restrict the domain from negative pi over 2 to positive pi over 2, then I have a strictly increasing function, which makes it monotonic, which makes it have an inverse. Okay? So negative pi over 2 to pi over 2 on that one. And if you think back to when you took pre-calculus and you learned about all your trig functions, we did restrict it. We restricted the domains on these trig functions for this reason. So we'll come back to this pretty soon, but not today. The derivatives of inverse functions. These are some properties that are pretty important, and if you understand them well, it will serve you well when you have to answer questions on tests. So, first of all, if the function is continuous over its domain, then the inverse function is continuous as well. If a function is increasing over its domain, then its inverse function is as well. If a function is decreasing on its domain, just like number 2, number 3, then the inverse is as well. And number 4, if the function is differentiable on an interval containing some number c, and the derivative at c is not equal to 0, then the inverse function is also differentiable at c. Why would this little rule need to be applied here? So, picture what this one's saying. Function's differentiable, great, on an interval containing this number right here. So, if I take the derivative at that point, I'm finding the slope, right? And I'm saying as long as the slope at this point is not equal to 0 in the original function, then the inverse will also be differentiable at c. Well, why would it not be differentiable if the slope at that point was 0? Why would the inverse not be differentiable if the slope at that point was 0? What do you mean by there's no x? Oh, I see what you're saying. So if you had a horizontal line and you traded the x and the y, there was no x to switch. That's an interesting thought. I never thought of that. The answer I'm looking for is, from Algebra 1, our slope equation is what happens if I swap the x's and y's? You'd have division by 0, yeah. Because if I wind up with a slope of 0, then this numerator is 0. But when I find the slope of the inverse, the x's and y's have swapped, which makes the denominator 0, which makes division by 0, which I can never do. So that's why this little rule is important. As long as you are not talking about a slope of 0, then you can find the inverse. You can take the derivative of the inverse at that point. Because it would become a vertical slope. Right. Okay, so better? All right, concepts, very important right here. Okay, let's take a look at this problem. The graph the inverse functions f of x equals x to the third and g of x equals x to the 1/3. I'm actually telling you that they're inverse functions. And then we're going to calculate the slopes of f at these ordered pairs and the slopes of g at these ordered pairs. Now first, before we get into this graphing situation, what do you notice about these ordered pairs? Yeah. So F and G are inverses of each other. And then the ordered pairs that I'm giving you are all traded from here to here for X and Y. I swap the X and the Y. Okay? So we're going to take a look at what happens when we look at ordered pairs that have been swapped, comparing them to original function and inverse. Okay? So let's graph both of these functions and take a look at what they look like. And then we'll talk about what those ordered pairs are. We can do the ordered pairs analytically instead of graphically. All right, the graph of x to the third is this blue guy, and then the graph of x to the 1/3 is the red guy. Now, based on the stuff that we've seen with these 4 ideas right here, take a look at this last one. Do we have a spot where the slope of the original goes horizontal? And then, therefore, if we look at the graph, do we have a spot where the slope goes vertical? Yeah. Is the function here, the blue function, is that continuous? Yeah. Is this one continuous? Yeah, it is. Can I differentiate everywhere on this function? On this blue one? Yes, I can. Can I differentiate everywhere on this one? No, I can't. Because of that one spot where it goes vertical. Okay? So that's what that last one right there is kind of getting at. So just kind of picture in your mind what's going on. Okay, F is continuous on its domain, then F inverse is as well. This one is continuous, so is this one. If F is increasing on its domain, then F inverse is as well. This one is always increasing, so is this one. Okay? Now, we're not decreasing, so we can't look at 3, but the same idea is true there. So that's what those 4 things are trying to say. Okay, so let's take a look at these ordered pairs now. F at 1, 1, 2, 8, 3, 27, and then for G as well. And is it F or F prime? Calculate the slopes of F. Okay, so what are we doing here? Good. So the derivative of this guy would be F prime of X equals 3x squared. And the derivative of this guy would be G prime of X equals 1/3, I like, X to the negative 2/3. Remember, we're taking the derivative, so you're subtracting. So I can rewrite this, and I want to. What do we actually have here?
1 over 3x.
Yes. Okay. So now that we know what the derivatives are, we can easily analyze these 3 ordered pairs for each. So at 1, 1, what is the slope for F? It's 3. At 2, 8, what's the slope? Okay. And for 3, 27, what is the slope? Yeah, 3 squared is 9 times 3 is 27. Okay. Easy part done. Now, what is the slope for G at 1, 1? It's 1/3. And what is the slope at 8, 2? So remember that we can apply the cube root first and then square it, or we can square first and then cube root. I prefer the cube root first when I'm dealing with a perfect cube because it makes my numbers smaller. So the cube root of 8 is 2, squared is 4, 4 times 3 is 12, so we have 1/12. And then how about 27 comma 3? You're going to guess it's 1/27th? Just a guess? It is 1/27th. So, let's answer this question right here first. What do you observe? The slopes are, there's a better word than inverses. Multiplicative inverse is a fancy way of saying an R word. Reciprocal. Yes.
Reciprocal.
The slopes of inverse functions are reciprocals of each other at corresponding x values. This is a concept that is critical that you understand for inverse functions. So I'll probably write that down for what do you observe. Make sure you know that the slopes of inverse functions are reciprocals of each other at corresponding x values. I shouldn't say corresponding x values, because it's not really corresponding x values. Corresponding ordered pairs would probably be better to say, because really what happened here is in F we had 1, 1, 2, 8, 3, 27, but in G we had 1, 1, 8, 2, 27, 3. So when you swap the ordered pairs, then you get reciprocal slopes. Okay? What happens at 0, 0? The world explodes. So at 0, 0, we'd have f prime at 0. What do we get? Plug 0 in and we get 0. But we'd have g prime at 0, which would be 1 over what? 0, which is undefined. So, yeah, the world just ended there. But the point is, this number 4 came into play there. We got a slope of 0, which means that we're in bad shape for number 4. Okay? So just keep those 4 things in mind, and then understand that inverse functions have reciprocal slopes when you swap the x and the y values. This is a very important theorem. It is on the AP exam. It's on there usually once, maybe twice, but that's 2 problems that you can get right if you understand it, and 2 problems that you will definitely get wrong if you don't. The derivative of an inverse function. So we let f be a function that's differentiable on an interval I. Interval I doesn't really matter, whatever, it's just an interval, okay? So kind of don't worry about that part. If f has an inverse function g, so we're saying that f and g are inverses of each other, then g is differentiable at any x as long as f prime of g of x is not equal to 0. What that's saying is as long as we're not taking the inverse when the slope of the original was 0, like we just talked about. Okay. So that's the theorem right there. Or this is the language of calculus instead of in words. G prime of x equals 1 over f prime of g of x, as long as f prime of g of x is not equal to 0. So that's the theorem. But what does it mean? I will say that the way that this is written is incredibly confusing. It confuses the heck out of me. It confuses the heck out of everybody when they see it. And it's really tough to understand it written like this. So what I'm going to do is try to change the way that this is written. This is the book's definition right here, and the book's way of writing that theorem. So I'm going to try to change the way that this is written so that you hopefully will understand it better. Okay? It starts by taking this first statement right here. F is a function, and its inverse is g. So what that means is g is f inverse of x. It's a subtle thing that went on from here to here, and it's easy to lose that. Yeah, this should be minus 1, not prime. Sorry. It did say f inverse, though. Yeah, if we define f and g as inverses of each other, then g is f inverse of x. It's kind of like saying y equals f of x. G is f inverse of x. Okay, so now that we know, I could put g of x equals f inverse of x. So that would be probably the best way to write it. So now that we know that, then what is g prime of x? This is our inverse function's derivative. But if I don't write it with the g, I just want to use f because just writing this thing in terms of f is going to be a lot clearer than what we have here. So I want to turn g prime of x into something as an f of x. So what would I write for that? F inverse of x. And I want to write that as, oh, wait, let me fix that too. Sorry. I'm going to write that as f inverse prime of x. Okay? Because g of x is f inverse of x. Therefore, g prime of x must be f inverse prime of x. Okay. Equals. We still have the 1 over. F prime of x, or f prime, still is f prime of what though? F inverse of x. Good. This is a comma right here. Sorry. Yeah. Now, we need to change this also. What should this say? F prime of f inverse of x can't be equal to 0. I like this format better because we know what f prime is and we know what f inverse is, which means we know what f inverse prime is also. But when you start throwing that g in there and that g prime, it gets confusing and it's easy to lose track of what it is that you're talking about. So what we have here now is the derivative of the inverse function is equal to 1 over the derivative of the original function composed of the inverse function. This is like Fogg or Goff right here. 1 over Fogg or Goff. So what that means is, if we take the derivative of a function, what are we finding? Slope. So the slope of the inverse function is equal to 1 over the slope of the original function at the inverse, which is basically what we said on the last page when we said that the slope of the original is the reciprocal of the slope of the inverse. 1 over something is the reciprocal. Okay? So that's all this theorem is saying, is that the slope of the original is the reciprocal of the slope of the inverse composed within the original here. Okay? That's it. So I don't know if I said that quite right, but that's all that's going on here. That's what that theorem says. So if you keep that thought in mind, hopefully you'll be able to do this a little bit easier. So if we go back to what we first talked about, if I have an ordered pair and I find its reciprocal, then the ordered pair would switch. Correct? Okay. If I find its inverse function, the ordered pair switches. But if the slope of my original function at x comma y is like a over b, let's say, then this theorem right here tells me that the slope here is going to be b over a. That's basically what this says. That's the concept behind what that theorem is trying to tell you. Okay, so now the nice thing about this theorem, or the brutal thing about this theorem, I guess, depending on how you want to look at it, is I can apply this theorem to just ordered pairs. I don't have to have a function, which means I don't have to find the inverse function to apply this theorem. So I can give you something that looks crazy like this. Would you be able to find the inverse function of this if I asked you to? In terms of y? Y equals some stuff? Why not? Yeah, you'll have x equals 1/4 y to the third plus y minus 1. Go ahead and solve that for y. You can't. Okay? So that's where this theorem comes in really handy. And it gets to where I don't even have to give you a function to begin with. If you understand the theorem well enough, I can just give you ordered pairs and maybe a derivative or something. That's how you're going to see this theorem presented on the AP exam. It's just going to be ordered pairs. They'll say f is blah, blah, blah. What is f inverse at such and such. And you're applying this theorem to that. So let's go ahead and do this problem here, and hopefully then we can understand, before the bell rings, what it is that this theorem does for us. So we have this function f of x equals that. First, what is the value of f inverse of x when x equals 3? That's right. We need to find f at 3. Because then we'll have an ordered pair. We'll have an x comma y. And then I'll be able to find f inverse at x. Because all I have to do is swap those coordinates. Okay? So now the question is, how do I find f at 3? We plug it in. What? Mm-hmm. No. That's not what we do. Yes, that's what we need to do. We need to find when the equation equals 3. Because we're going to have to switch the x and the y. So this right here is actually going to be 3. Yeah, kind of. So what we have is 1/4 x to the third plus x minus 1 equals 3. Now what? How about subtract 3? Because you've got to solve for x now. And the way that we solve for x is by getting everything on one side and equals 0 on the other side. So I'm going to subtract 3 from both sides. So 1/4 x to the third plus x minus 4 equals 0. Now what? You could live the next hour of your life in Algebra 2 and do Descartes' rule of signs and all kinds of other things. Or you can't use the quadratic formula because that's a third power. How about you graph it and you find where the graph crosses the x-axis? That's not cheating. That gives you a value for x. We'll get a value. X equals something. What is it? X equals 2. So yes, we took this equation right here and solved it for x by graphing it. I don't know what the graph looks like, but it crosses the x-axis at 2. So therefore, when x is 2, this equation is true, which means that 2 is my answer. What is the value of f inverse of x when x equals 3? It's 2. Now what is the value of f inverse prime of x when x equals 3? Well, using this notation right here, and using the way that I rewrote that, f inverse prime of x is what I'm looking for right here. So that means I can just write down, I can use that formula right there, that theorem. F inverse prime of x equals 1 over f prime of f inverse of x. But f inverse of x is 2. So what I have is 1 over f prime at 2. Well, how do I get f prime at 2? Take the derivative of f. And that's an easy one that we can do. 3/4 x squared plus 1. So now I have 1 over, so that's 4. 3/4 times 4 is just 3, plus 1 is 4. So the answer is 1/4. Hopefully you don't think it's too bad, but what you need to do is remember that this question is actually asking you if x is 3 in the original function, then what I'm doing with my inverse function is I'm calling that a y. because I swap from the original to the inverse. I swap my x's and y's. So this x is actually a y here. So that's why I plug in that 3 here. I can graph it. I have a function, I can graph it. If I don't have a function, if all I have is ordered pairs, then that changes things, but the idea, the concept here is still the same.